Good morning. Can you all hear my voice?
Morning, sir.
We will, I think, we will start the class, okay? And for today, right, we will concentrate on the friction. Okay, so for today, we will start discussing about the friction. Can you see my slide right now?
Yes, we can see it, sir.
Okay, I think I will start the discussion on this. Okay, I started the screen recording already. So about friction, right? This is one part of things that actually there in our life, and I believe that you have learned about this for quite a while as well. Okay, I think let's. Okay, let me start the recording. So friction, it's been there in our life, and I believe that you already learned about friction in your last semesters as well, I believe. Correct or not? In the physics subjects. Hello, Sip?
Yes, Pak.
Yeah, you're fine. Okay, see. Thank you. So I believe you have learned about it. So most of the topics about friction is has been discussed before in the physics class, but for today I will start the discussion on the friction in more detail regarding the things that is related to the statics problem. Okay, and in reality, actually there are three types of friction, as you can see here. Okay, dry friction, which we will study deeper in this particular statics in our statics class. Then fluid friction. Okay, it's a friction when it's involved fluid. Okay, for example, like what you see here, when somebody is swimming, and that guy will receive friction from the water. Okay, and then we have as well internal friction, which is happening inside of the material. Okay, landslide here is a example when the internal friction got less and less, and then that's why, because the friction, internal frictions get less and less, then it will slide to each other and it becomes landslide like that. Okay, so those are the three types of the friction, but most of the time we will concentrate on this dry friction. Okay, and this is the mechanism of the dry friction. Previously in the physics, I believe this is what you learn. Okay, you expect everything to be in the all the things, right? We assume it as a point. Okay, we assume the things as a point. What I mean as a point is we don't consider the length and the width of the things that is under friction. So the height here we don't consider about it. The length here we don't consider about it. The width as well we don't consider about it. So whenever we talk about friction in physics, previously, okay, we always thought that things as just one particle point, okay, where all the things happening on that particular point. So the friction force which is happening at this particular things only happening at one particular point as well, due to one particular force which is normal force. So previously we have it like this, right? If we draw the free body diagram, right? The previous one, we have the weight, we have the force P, and then we have the normal force, and then we have friction force. Okay, and we assume everything happening at the same location, at the same point. Okay, and that's one of the assumptions that you did before in the physics. I'm not sure whether you learn about physics in the last semester or not, but I believe if you learn, most of the time the discussion will be like this. Okay, and the same as well, if we are talking about the friction that you learn in the physics in your high school year, okay, I believe everything, all the discussion there is when you talk about friction on a particular things like this, you assume that everything happening, all the forces happening at one particular point. That's why whenever we talk about friction, we don't talk about moment, which is caused by the friction. Okay, that's the thing that you learn in high school. Okay, but actually, in reality, what is happening is not like this. The normal force is not just happening at one particular point like this. And the friction force is not just happening at one particular point like this. Okay, so basically, what is really happening is the normal force is distributed. Okay, the normal force is distributed along the ground here, the ground contact here. And because normal force is distributed along the ground contact there, that is why the friction will be distributed as well on the ground contact there. Okay, so both the normal force and the friction force actually are distributed on the ground contact. So if the things here, this rectangular box here is in contact with the ground on this particular part, that's why here at this particular part, right, the normal force are distributed and the friction force are distributed as well, and not necessarily, okay, it is a constant distribution. Not necessarily it is constant distribution. Most of the time the distribution is like this, okay, following a linear distribution, but sometimes it's not even linear, but it's not constant as well. Okay, so so that's the thing that is different from what we learned in the high school and what we learn now about friction. So now we try to learn friction in a deeper way, like that. Okay, and if we see deeper on what is actually really happening here on the ground contact, which is happening between the things, the square things there, sorry, the rectangular things there and the ground. Actually, this is where it's really happening. If we zoom in, right? If we zoom in a certain part here, for example, here, this is why it's really happening. So basically, friction, dry friction, is happen. Dry friction happens because of the rough contact. Okay, rough contact between two surfaces. So the top surface here belongs to this rectangle things, and the bottom surface here belongs to the ground. And both actually are rough. Both are actually rough. And those rough surfaces, when both are in contact, okay, it will produce friction. And if you know, right, between one materials and several different materials, for example, the box here, for example, is made of stainless steel. Okay, and the ground here made of concrete. Okay, if the box is made of rubber and the ground is made of asphalt, for example, okay, the friction coefficient between these two and the friction coefficient between these two will be different. Why those are different? Because the interaction between those two surfaces will be different as well. Okay, this surface and this, right, the interaction between those two and the interaction between this and this will be different. Most of the time, the one that will affect it the most is this, the roughness of both surfaces. Okay, the roughness of both surfaces. One material and the other material will have different roughness of the surfaces. Okay, stainless steel, which receive the special treatment on the surface, will be different than stainless steel, which is not receiving any treatment on the surfaces. Because if it is treated on the surfaces, if it's treated on the surface, okay, the roughness can be less than the normal, something like that. So the friction coefficient, okay, that you learned before actually depends on the roughness of both surfaces. Besides that, it will depends as well on the type of the materials. Besides on the roughness, but it will be affected as well by the type of the materials of both surface. So actually, that's the thing that is new in this particular statics discussion on the dry friction. Okay, so basically, if you see, zoom in, all these normal forces and friction forces will be happening here. Okay, and the friction force will be happening there as well. And you can see here the normal force, which is happening at each contacts, small contacts, will be different, and the friction force, which is happening at those small contact, will be different. So actually, even though the distribution is quite close to linear, but it won't be exactly linear. Okay, it will be slightly random as well, but most of the time we can approach it with a linear distribution. Okay, up until this point, any question? This is the new discussion on the dry friction. And previously, yes, you have learned about dry friction, but I believe the discussion has never been this deep before. Any question here? Rizky, do you have any question? Sik? Sunita?
No questions, sir. Thank you.
Okay. Sik, okay, because you are answering me just now. Last semesters, did you learn about friction, Sik?
Yes, sir. About
But
yeah.
the discussion on the friction is if all the forces are happening at one point, right?
Exactly, sir.
So there is no moment happening there, right?
No, we didn't yet. We didn't study about that.
Okay, good. So that's the things that will be different from what you learned last semesters and what you will learn in statics. Okay. I think in that case, I will just continue. So this is actually what is happening in reality when you have two things in contact to each other, and then force P is given to one of the things. Okay, so there will be a friction force like this. Okay, remember that the distribution will not be constant. Okay, the distribution will not be constant. The distribution will be closer to a linear. Although, if we take a look closer, it's not exactly linear, because what is actually happening is it will be slightly random, because everything will depend on the contact, the small contact, which is happening between those faces. Okay, I think I will continue. But if we have to discuss all the friction things, all the normal force thing, using this kind of distribution, it will be too complicated for us. Actually, it's not that complicated, but it will be too long for us. Okay, so as what you learned before, okay, as what you learned before, this kind of a distributed force, remember, right? Previously, we learned about it. When we have a distributed force like that, we can represent it with a representative concentrated force. Okay, representative concentrated force at certain at which is happening at the COG. Okay, which is happening at the center of the area. Okay, the COG of the area. So, for example, we can represent this friction force, normal force here, and at the same time, we represent the friction force at the same point as well. Okay, so that's the thing that we will try to implement in the current statics discussion on dry friction. So instead of solving it like this, like what is really happening, okay, we try to find the COG of the normal and the friction force, okay, based on the distribution. Then after that, we will represent the normal force and the friction force at that particular point. Something like that. Okay. So this is the example. Okay, this is the example. For example, we have force P here, which is happening at a box, stainless steel box, like what I said before, which is which is placed on top of concrete like that. Okay, and if we take a look at the free body diagram of the metal box, okay, this is what you will find. Okay, this is the representative. This is the easier way to represent what is really happening at the metal or on the metal box. Okay, which is really happening on the metal box. So there is a force P, there is a weight there in its center of gravity. Then there will be a normal force resultant, and there will be friction force resultant as well there. And the resultant will be in the x direction to the centers. It will be in the in a distance x from the center, like that. Why? Because, like I said before, actually the normal force in reality will be in the shape of a distributed force. Okay, and the distribution is closer to linear. That's why it will not be exactly in the middle. So it will be in the x direction from the middle, as what you see here. Okay. Then after that, if we try to okay, so basically, why the normal force will be in the x direction, x distance from the center, like that? It's mainly because if you can see here, okay, the P here and the friction force here, okay, if everything in the static equilibrium, there will be a couple. Those two forces are coupled. Okay, so it will create moments, clockwise moment there, due to P and F. Okay, and then W and N, it's supposed to create another couple. It's supposed to create another couple, and in order for the things to not rotating, okay, the couple here supposed to have the direction of a counterclockwise direction to neutralize what is happening to this, like that. So from P and F, it will be clockwise moment. Okay, from W and N, it will be counterclockwise moment, and the value of both moment supposed to be the same. Okay, the value of both moments supposed to be the same. Why? Because if it's not the same, tipping will happen. What I mean by tipping means when you give a pulling force P there, okay, the box, instead of moving horizontally or instead of just staying still, okay, what happening there will be it tips, it rotates like that. Okay, I believe you have done it before. For example, you can see here. You can see in my video. There is a CDR box. There is a CDR things here, right? When I push it, okay, if I push it at the bottom, okay, it will move, right? But if I push it at the top, okay, it will tip over. This is the phenomena which I call as tipping. Okay, what is really happening there is the pushing force here, P, and the friction force there, it will create a moment. And the moment is bigger than the weight W, the moment which is caused by the weight W and the normal force. That's the thing. Okay. So basically, as everything's, all the things are trying to okay, as we are talking about statics problem, okay, as we are talking about statics problem, when we have force P and friction force F here, okay, and if in reality there is no tipping, for sure, okay, the moment which is caused by this have to be naturalized. And how can we naturalize it? W must be happening at the center of gravity. So how can we naturalize it? We can naturalize it by moving the force N here to a distance x from the center, like that. By doing so, you will create a moment between these two, and this the moment between those two must be the same as the moment which is created by these two, but in the opposite direction. That's the logic behind that. And after you do so, what is really happening is you will find the location of the normal force. Okay, the location of the normal, you will find the representative resultant of the normal force. Okay, what you will find is the resultant. You will find the resultant of the normal force. So basically, what you find there is the resultant of this particular distributed normal force. It will be here. So instead of calculating it from the distribution, like what we did before, okay, we know this is the distribution, and we know this is the distribution, and because the distribution is like that, then we can calculate where's the resultant, where's the location of the resultant. It's not like that. But instead of doing so, what you did is try to calculate it directly based on the other forces which is happening there to get the value of x here. So the value of x here will depend on all other forces plus this h as well, the location of the pulling or pushing force there. Up until this point, anyone want to ask question? Up until this point, anyone want to ask question?
Sorry, Pak. What's RS in between N and FS?
Oh, RS, it's the things that I will talk about later after this. So that those two are the resultant of the friction force and the normal force.
Okay.
So if you sum friction force and normal force, that's what you will get. Okay, but even without doing so, even without doing this, okay, even without doing that, you will still be able to solve all the things here, like what I told you just now. But the one that I want to ask you guys is whether you understand why the normal force, okay, in reality will not be happening at the center here. Okay, the normal force will not be happening at the center here, Okay, when the pulling or pushing force has distance with the friction force, has certain distance with the friction force. So that's the reason behind the normal force is not happening at the center when there is H here. It's because there will be a moment, okay, and the moment need to be balanced out. And how to balance it out? By moving the normal force, by moving the normal force, okay, and because of that, because you move the normal force, there will be a couple, there will be a moment, and the moment will balance out the moment which is caused by this. Okay, this is how we analyze it. This is how we analyze the problem. Okay, but behind the scene, what is really happening is like this. But of course, if we have to put the distributed force for the normal force, this normal distributed force, and the normal distributed friction force there, the calculation will be too long. So we do it straight. We do straight away like this. So this is how we will analyze things for this dry friction. Any question on that?
No, sir. Thank you, sir.
Okay. How about you, Rizky? Hello, Rizky. Don't sleep again, Rizky.
I think he's still in bed, sir.
Yeah, most likely like
But
that.
he's still attending class, but cannot talk.
Which means that he sleep again, right? Not sure. Okay. What else here? Aser, do you understand, Aser? Hello, Aser. Ashar. How about you, Ashar?
Yes, sir. Hello.
Do you understand?
Honestly, not yet too much, sir.
Which part that you don't understand, Ashar?
Previously, I was on the toilet. I had a stomach ache, so I didn't hear explanation. I just got back.
Oh, okay then. So later, don't forget to rewatch the video, okay?
Okay, sir.
Shabina, do you understand, Shabina?
Yes, sir.
Okay, good. Okay, I think in that case, I will. Hello, Lalu. Yes.
Sir, I have a question. I'm not really understand about the W, and for the
W is the weight. Why you don't understand about W?
Oh, okay.
The weight of the things always there, right? W is the weight of the things. It's always at the center of gravity, right?
Oh yes, sir.
So previously, what you learned before, W is in the middle, in the center of gravity, then normal force in the middle as well, because everything happening at one point, but that's not really happening. So what is really happening is like this. Okay, W will be in the shape of a concentrated force, and then P, the pushing in the pulling force, will be a concentrated force. But when we talk about normal force or friction force, it's actually a distributed force. Both are distributed force. Okay, normal force is the distribution is like this, vertically. Okay, and most of the time it will not be constant, so it will be somewhat close to linear, even though it's slightly random. Okay, and the friction force, it will distribute as well, although the direction is horizontal, but it will be distributed as well, and the distribution will be close to linear as well. Okay, but if we have to analyze it like this, it will be too long. So what we do is we represent both normal force distribution and the friction force distribution. We represent both with concentrated force. So normal force will be concentrated at one particular point, and friction force will be concentrated at one particular point. That's the thing that we will try to calculate: the location of the normal force and the location of the friction force. How to find the location of the normal force? That's the question, right? The question is by using the moment equilibrium. Okay, the normal force here, when in real condition, okay, when in real condition, the when you give a pulling or pushing force, the thing is not tip over like what I show you just now with my CDR here. Okay, if it's not tipping over, it means that the moment which is caused by this P and friction force pulling the force P and the friction force, it will be neutralized by the moment due to the weight W and the normal force N. Okay, by doing so, by doing all the calculation, you will be able to find the distance x there with condition of distance h here is known, P is known, W is known. Okay, using sigma fx equal to 0, this is what you will get. Friction force will be equal to P. Using sigma fy equal to 0, this is what you will get. Normal force is equal to W. Okay, and using sigma moment, you will be able to get this x distance there. So we will still try to solve this using our equilibrium equations. Sigma fx equal to 0, sigma fy equal to 0, and sigma moment equal to 0. By doing so, you will be able to find all the unknowns. Do you get it?
Okay, sir. I can imagine.
Okay, any other question? If not, then I will try to continue. Okay. So as you can see here, just now, like what Matthew asked, what is R here? RS there. So basically, you can represent the normal force and the friction force with individually, like friction force is F here and normal force is N here. But you can as well represent both normal force and friction force using RS here. Okay, why it's like that? So actually RS is actually the resultant of the friction force and the normal force. Why we can do it that way? Because you must remember that friction force is actually normal force multiplied by mu. Okay, where mu here is actually our friction coefficient. It can be mu s. Okay, it can be, sorry, this one is not fs. And friction force F. Okay, friction force F will be equal to normal force multiplied by mu, where mu is the friction coefficient. Okay, mu is friction coefficient. That is why, okay, when the condition is not changing, okay, when the condition is not changing, for example, when it's not still not moving or something like that, or or impending motion like that, or when it's moving in constant velocity like that, then you will find out, right? So you will find out that friction force and normal force, okay, friction force and normal force is actually having a relation like that. Okay, there are several conditions when friction force and normal force has a certain relation. The first one is when it's slightly about to move, impending motion. When it's in impending motion, the friction force will be in its maximum value. Okay, and the value will be equal to normal force multiplied by mu s. What is mu s there? Mu s is a static friction coefficient. So this is the maximum value of the friction force. And it's happening slightly before it moves, so impending motion. Okay. So the other time where friction force and normal force will have certain ratio will be when the things is in motion with constant velocity. When it's in motion with constant velocity, it will follow this. Okay, Fk, okay, friction force when it's moving, equal to normal force multiplied by mu k, friction coefficient when it's moving. Okay, so these two conditions are the condition where the friction force and normal force has a certain ratio, and the ratio will depend on the mu s and mu k, like that. Okay, so as you can see here, the free body diagram of the things when it's just slightly before it moves, or impending motion. The meaning of impending motion is when it's slightly about to move, when the friction force in its maximum state. Friction force here is equal to normal force multiplied by mu s. Okay, this is the free body diagram. Okay, Fs and N, we can get the resultant Rs, and Rs will have an angle of Vs here. Vs here, it will have direct relation to mu s, which later I will teach you guys for. But even though without doing so, you can still analyze the friction force or normal force individual without doing it like this. Okay, because the resultant, you can put it as one resultant like that for friction force and normal force, but if you want to separate it, you can as well. And it is much easier to solve all the things by separating both. Okay, any question about this? No? Okay, in that case, I will just continue. So this is one of the example of the tipping effect. Later, I will put this on the on one of your homework. Okay, I will put this on one of your homework. You can see here at certain sorry, as you can see here, okay, there is one person who push the box like that. Okay, there is one person who push the box like that. Okay, and if we want to draw the free body diagram, the pushing force here we can represent it as a P. Okay, and then the weight of the box will be happening at the center of gravity. Okay, and then there will be a friction. There will be a normal force at x distance. Okay, and then there will be a friction force like that. Okay, the moment due to P here, because the height here is supposed to be known from the problem. Okay, the moment due to P and friction force, okay, will have to be neutralized by the moment due to W and normal force here. Okay, so if H is known, we can calculate for X. Okay, so the moment there, you can see that P and F will create clockwise moment. W and N will create counterclockwise moment. So it's supposed to cancel each other out. And in order to calculate for X there, distance X there, it will be very simple because we have two couples. The first couple is this, and the second couple is this. Okay, then we just need to calculate the moment due to both couples. So P multiplied by H, this is the first couple, will be equal to W multiplied by X. So X supposed to be equal to PH divided by W. Like that. Okay. But there is a certain condition here. So X will depend on these three, right? P, H, and W. Okay, P, H, and W. So if P is too big or H is too high, okay, if W is a constant like that because of the weight of the box is constant, if W is constant, then everything will depend on P and H. Okay, if H is constant, then that's it. But P here can be varied. So if P is too high, okay, there is a possibility that value of X here will be very big, will get bigger, because by increasing P there, the value of X will get bigger. It will be moving to the right. If P is getting bigger there, okay, with assumption of H and W is constant, if P is getting bigger there, then the value of X will be moved to the right. Okay, X there will be moved to the right. So normal force will be moved to the right. And it can only be moved until it reaches the NH here. Okay, it can only be moved until it reaches the NH there. Why? Because it is not possible for us to have normal force outside of the body. So it's not possible to have normal force here. It's not possible. So the maximum that we can do is the normal force is at the edge here. Okay, the normal force is at the edge there. And when it's happening, It's actually the condition when tipping is about to happen. So the condition when tipping is about to happen is where if you calculate the x, okay, the x will be big enough, okay, the distance x will be big enough, so the normal force N is being placed at the edge like that. Is being placed at the edge like that. What's the meaning of it's being placed at the edge? It means that it cannot be moved further because if it is not possible for normal force to be outside of the body. So, and beside that, this condition is the condition where tipping is about to happen. Okay. If you calculate with certain condition, for example, P is we have a certain value of P, certain value of W, certain value of H, right? And you find out that X makes the normal force outside of the body. For example, okay, this is the results of the X like that. So the normal force will be outside of the body. This condition means that tipping is happening. Tipping is happening. Sorry. So the box is tipping over. Okay, but if the location is at the right edge like this, okay, if the location is at the right edge like that, it just means that impending tipping, something like that. Tipping is about to happen. Okay, because it is the maximum location where normal force can be placed like that. If after you calculate, the normal force is still between the center here and the edge like this is between those two. So for example, like this, okay, it means that tipping is not happening. So it's still in the static equilibrium. This one is static equilibrium. This one is impending tipping. Okay. And if I have to draw another one, okay, this is P, this is W, P with certain H, okay, this is the center, okay, and after that you find out that the normal force is here. So the friction force is supposed to be there as well. It's not possible, okay, because the X is too big, for example. It's not possible. Because of that, right, this condition, when you have a, after you calculate, the condition is like this, it means that it's actually tipping over. This one is tipping over condition. Because this one is not possible. So the maximum is this one. This is the maximum. This is impending tipping. Okay. Any question about the tipping effect here? So as you can see here, right, the tipping effect, okay, will depend on the magnitude of the force P. When it's getting bigger, the possibility of it tips over will be bigger as well. The value of W, when the weight is getting bigger, the possibility of tipping over it will be less. And the last one is H here. When the height of the given force is very high, then higher, then the possibility of tipping will be higher as well. Will be higher as well. Okay. Any question here? Any question here?
No, sir.
Okay. Rizky, have you woken up? Rizky. Not yet. Okay. Darian Patrick,
Yes, sir.
do you understand?
Uh, for now, yes, for the tipping one, but I might need to rewatch the video again.
Okay. Yeah. Fasadiara, do you understand? Hello, Fasa. Okay. How about Florencia Irena? Do you understand? Halo?
Iya, yes sir. Halo,
Kamu ngerti Florencia?
iya Pak.
Oke, sip. Pasha,
Yes, sir.
do you understand?
Yes.
Okay, good. Okay, I think in that case, I will continue then with the with our next discussion. So this is about tipping effect, and the next discussion is about static and kinetic friction. Previously, I already discussed a little bit about static and kinetic friction. Okay. So basically, I believe you have learned about it in high school and last semesters as well. Okay. So when the things here is not moving, okay, the maximum friction force that can be produced in this particular contact will be this one, Fs or Fmax, right, equal to mu s multiplied by n, where mu s is the static friction coefficient and n is the normal force. Okay, but when there is a slipping which is happening here on those contact, okay, slipping which means there is a movement, okay, there is a motion, okay, the friction force will follow this equation. Fk is equal to mu k multiplied by n, where mu k here is the kinetic friction coefficient. I believe you have learned about it in high school and in last semesters as well. Okay, but sometimes students make a mistake that when there is no motion, or means that the condition is not moving or static friction, okay, when it is asked what is the friction force which is happening here when there is no static, there is no movement, some students answer directly like this: oh, the friction force will be equal to mu s multiplied by normal force. It's not necessarily like this. Okay, mu s multiplied by normal force will only be happening as the friction force when, okay, when the condition is impending motion, which means that the motion is about to happen when the when the friction force in its maximum state. Okay, but most of the time, okay, but most of the time, if the p here, okay, if the p there, the effect of the p there will give will need to be balanced out. Okay, will need to be balanced out with friction force less than this. Then what you're supposed to get is just like this: F equal to P. If P is horizontal, okay, if the pulling force or pushing force is horizontal, then what you will get is just this: F equal to P. So as you can see here, if right, if the pushing force or pulling force is increased, right, at the beginning, the friction force will increase. Okay, the gradient is equal to 1 because friction force and pushing force will be exactly the same. Okay, so if the relation between pushing or pulling force with the friction force actually will follow this graph. Okay, at the beginning it will be a linear with gradient equal to 1. Okay, until it reaches condition of impending motion. Impending motion means that the movement is about to happen, which means that the pulling or pushing force, the value will reach the maximum value of friction force, which is equal to mu s multiplied by n. So impending motion. Why impending motion? Because we cannot we cannot increase the value of p anymore because it already reached the maximum value of friction force. Then, if you keep increasing the p value, then motion starts happening. While when motion starts happening, okay, the friction force will get reduced because the value of the mu s and mu k, right? Mu k here, most of the time, for most of the materials, is lower than mu s. That's why the kinetic friction force will be lower than our maximum static friction force. Like that. So when P get increase again, the value of the friction force will be lowered like that. Okay. So the condition we can there are 3 conditions which we can differentiate here is where when there is a no motion, okay, friction force is equal to P, and then that's the first condition. The second condition is impending motion when the P is equal to the F max equal to mu s multiplied by n is impending motion. That's the second one. And then the third one is when motion happens. The third one is when motion happens. Okay. The value of P, okay, P is bigger than the friction force which is happening. Okay, where the friction force follows this equation equal to mu k multiplied by n. About these 3 conditions, anyone want to ask question?
Pak, so impending motion is the motion just before moving and tipping over, yeah?
No. This one is impending tipping.
Oh, okay.
So this one is impending tipping. So it's you have to differentiate it. So this one is because the moment equilibrium, right? Because the calculation of the moment equilibrium will cause the normal force and friction force happening at exactly on the edge like that. So it's impending tipping, just before tipping happening. But this one is impending motion, just before motion happening. So when impending motion happen, okay, when in the condition of impending motion, the the condition of impending motion is the pushing of the pulling force, right, is the same value as the maximum friction force, mu s, like that, mu s multiplied by n. If the free body diagram is like this, okay, because sometimes later the free body diagram will not be exactly like this. The P can be slightly slanted like that. In that case, the equation will not be F equal to P, or it will not be like this as well. So we have to calculate for that. But basically, impending motion means that the friction force which is happening is the maximum friction force, which is equal to mu s multiplied by n. Why we call it as impending motion? Because we cannot increase the friction force anymore. It's already in the limit. So when the pushing of the pulling force get increased again, then at that time, motion starts to happen. You understand, Matthew?
Yes, sir. Thank you, sir.
Any other question? About this? Okay, no? In that case, I will continue. So this is the friction angle that I talked before. Okay, this is the friction angle that I talked before. When impending motion is happening, okay, the friction force which is happening will be equal to mu s multiplied by n. Okay, so if we have this force as n, and if we have this force as fs, friction force, maximum friction force, maximum static friction force, then the ratio between those two will be in a certain number. The ratio between those two will be in certain number. That's why the angle here, Vs, will be in certain value as well. And the relation between Vs and µs will follow this. Okay, Vs, okay, as you can see here, Vs is actually arcus tangent of Fs divided by n. You can see, right? This one is Fs, this one is n. So arcus tangent of Fs divided by n will be equal to µs. Vs. Okay, and remember the Fs here, the maximum static friction force. It actually the same as this one, µs multiplied by n. Right? So I can replace this equation with this equation. Okay, and then I can cross this, the normal force. That is why Vs is equal to arcus tangent of µs. So if you want to represent the resultant force, okay, Rs of the resultant force of the maximum static friction force and the normal force, Rs here, okay, the angle there, Vs, it will be the same as arcus tangent of µs. Okay, the second condition where the ratio between the friction force and the normal force will be in certain value is when it's under motion. When motion happening. When motion happening, okay, when motion happening, okay, Fk here is the kinetic friction force, and here is the normal force. The ratio between those two will be certain as well. So we can represent Vk, okay, the angle of the angle here, Vk here. We can represent it as arcus tangent of this. This one is Fk, kinetic friction force, and divided by normal force. So it will be like this. Remember that Fk is equal to, Fk is equal to mu k multiplied by n. That's why we can replace this with this one. And then we can cross this and the normal force there. We can cross the normal force there. Okay, that's why we can get a relation, this relation. Vk is equal to arcus tangent of mu k. Okay, so this is the things when this is only happening. Okay, you can only represent this when when the condition is either impending motion using this equation, or when it's under motion using this equation. Okay, I think I will continue. So after this, there will be several problem example, but some of those problem I will give it to you for your homework. Okay, but first, before that, you have to know about the type of friction problem. Remember, I already discussed it before. Okay, there are only three conditions of a static of a dry friction. There are three conditions in the dry friction. The first one is impending motion is known to exist. This is a condition where friction force is at its maximum value, F max or Fs. Okay, so equal to m mu s multiplied by normal force. Then the third condition is when relative motion is known to exist between contacting surfaces. Okay, in this condition, friction force will follow this. Fk equal to mu k multiplied by normal force. And then the middle condition, the second condition is neither impending motion is known to exist or relative motion is known to exist. So actually for this one is the condition is in the static equilibrium, but not in the impending motion condition. So what you learned before is F will be equal to the P there, but this one depends on your free body condition. Remember, okay, if the free body condition, if the FBD free body diagram is like this, W is here, weight is there. Okay, sorry. Then pushing force is here, P. Then a normal force is here, friction force is here. Okay, if it's just like this, it will follow this F is equal to P. Okay, so there are three conditions. And if we talk about using this, right, the first condition is happening here. Okay, the first condition is happening there, here. When the friction force in the it is in its maximum value. The third condition is happening here, when motion is happening. The second condition is happening here, static equilibrium. Static equilibrium, but not in the impending motion condition, like that. Okay, so only those three conditions. And how to handle those three conditions, we can practice more for that. So this is the basic theory. This is the basic theory, all the basic theory about dry friction. Okay, so there are several things that you must know. Okay, why the friction force and the normal force will not be happening at the center? It's mainly because actually it's supposed to be normal force distribution and friction force distribution, and the distribution, it will not be constant. It will be linear, close to linear, with slightly random. Okay, and how to represent that? We can represent it as a constraining force. Okay, with certain distance from the center. Here, the distance is x, right? And in some condition, because the ratio is certain between friction force and the normal force, we can represent both with resultant force RS, resultant force R with certain angle. Okay, and then you must know as well about tipping effect. Okay, the tipping effect. So when you give a force like this, horizontal force like that, the normal force will be shifted with distance x from the center. Okay, but when P is getting bigger or H is getting bigger or W is getting lower, right? The normal force will be shifted again to the H, and the maximum it can be shifted is until it's until the H, okay, until the H here. Okay, this particular condition is, we call it as impending tipping. When tipping is about to happen, okay, because we cannot increase the value of P anymore, or we cannot increase the height anymore, the height of P anymore, like that. Okay, but if you keep increasing P values or height value, H value, right, the friction force and the normal force will be outside of the things, and it cannot, okay, it will not be happening. So what really happens there, it will tip over in that condition. This condition is tip over condition, this one, when friction force and normal force is outside of the things, like that. Okay, this is tip over condition. And we have another condition as well, whether it's in a static equilibrium, impending motion, or in a motion condition. Okay, in the static friction, if they the first condition is impending motion. Impending motion means that the friction force is in the maximum value, mu s you multiply by n. Then the third condition is motion condition, is when the friction force is equal to mu k multiplied by n. Okay, then the second condition is it is not part of impending motion or motion, so it's actually in the static equilibrium, but before impending motion happening. Okay, if the free body diagram is like this, F will be equal to P. So those are the three conditions, and beside that, if we talk about the impending motion or motion condition, the ratio between the friction force and the normal force will be certain, and it will follow this for impending motion, and it will follow this for if the motion happens like that. But without doing it like this, we still can be able to solve the problem. Okay, even without doing it like this, we still can be able to solve the problem. Okay, I think that's all about the theory behind the dry friction. If you have any question, you can ask me now before I discuss about the problem example.
Pak, for the one yang impending motion, impending tipping motion.
Impending
it only
tipping, yes,
applies
impending
to-
tipping.
Yeah, it only applies when Fs equals to P.
Sorry?
Yeah, for this one, it only will be applied when Fs is equal to P.
No, not necessarily. Not necessarily. It can be. We can do this when it's in the condition of we can do this in combination with this one as well. So when P is very small, too small, then it will be in the second condition. Then when P is big enough, okay, there is a possibility that it will be in the impending motion condition. But when P is too big, very big, Then there is a condition of the third condition, the same as when you are pushing a what you call it, a wardrobe or box like that. If you push it with enough force, it will move, right? But not necessarily it will move. Sometimes in some condition, instead of it's moving, it will tip over, right? Do you get it? Matthew?
Yes, sir. But how do we calculate?
So actually, there are several analyses that you have to do here. Okay, so you have to check whether it will tips over or not. At the same time, you have to check whether it will move or not. Okay, so tipping over condition and moving condition is separate things, but sometimes you have to do it at the same time. Do you get it?
Paham, Pak.
Yeah.
Yang bingungin itu how you calculate couple-nya from P and F if they're different in value. Because
but actually later there will be information there, right? So it depends on the problem. So later you can try to practice with the problem. I think I will give this particular problem in the homework, so you can practice with that. Okay. It depends on the problem. So for example, in the problem, it's the information is given like the condition is in the static equilibrium or something like that, or the equation, the condition is it's actually moving. You understand, right?
understand, Pak, understand.
Okay, so tipping and this static and kinetic friction is two separate things. So something can tips even if it is not in the impending motion condition. So it's not necessarily have to be this have to be connected like that, but sometimes you have to handle both at the same times, tipping effect and the movement effect. Sorry, motion effect. Okay. So we have when we talk about drive friction, there are two kind of effect. The first is tipping effect. The second is motion effect. The motion effect will affect the value of the friction force. Okay, the tipping effect will determine whether it tips over or not. Do you get it, Matthew?
Yes, sir, yes, sir. Bingung ini aja sih. Kalau misalnya dia moving,
Yeah, I
kan
know.
couple-nya different gitu.
So your question is, how can we know what is the value of f if it's not given from the beginning, right? Although just now I explained to you that.
Oh yeah.
Yeah. So actually, yes. Later it will be depending on the problem. Everything will be depending on the problem. Okay, Matthew?
Oh, so it's probably given juga ya.
Yes.
Okay.
Just try to practice with the problem later. Okay, but the basic theory, you get it, right? There is a tipping effect, there is a motion effect. So we call this as motion effect. Motion effect, there are three conditions. Impending motion, motion, or neither impending motion or motion. Okay, then there is a tipping effect as well, which means that it's in a static equilibrium condition or impending tipping or tips over. There are three possibilities as well for the tipping effect. One is no tipping at all. One is impending tipping. Okay, 3 is tip overs or tipping. 2 is neither impending tipping or tip overs. It's like this. This is number 2. Okay. There are several problems that we can use it as an example. Okay, I think I will start with the easiest one. So I think I will just stop this one.